So another way that we can look at this is we can use the number of moles of gas in the reaction to predict entropy changes. If we have more moles of gas, we get a higher entropy. Fewer moles of gas, lower entropy. We can also use the complexity of the molecules to predict entropy changes. If it's less complex, it has a higher entropy. Now, I had a little bit of trouble with this one at first when I was learning this as a student, because I thought if it's less complex, it should be just the way it is. But the way it works is, as you get bigger molecules, remember everything we learned in Chem 111 about bond angles and bond distance and things? And as you have those bond angles, as the molecules start to kind of twist around those bonds, the bigger you get, the branches start banging into each other. So as you get bigger molecules, they are sort of restricted in the conformation that they can take on. And that's something you'll talk about a lot more when you get to organic. But for now, you can just kind of remember less complex things have a higher entropy. So with all those ideas in mind, if we look at this, I have 2 moles of NO2 gas becoming 1 mole of N2O4 gas. So I'm going from 2 moles of gas to 1 mole of gas, so my change in entropy would expected to be negative. Here I have propane reacting with oxygen. I have 6 moles of gas on the left. I make 3 moles of carbon dioxide and 4 moles of water gas. So I would expect, since the moles of gas is increasing, that my entropy change would be positive. Here I have water gas going to water liquid, so I'm condensing things, so I would expect that the entropy change would be negative. So now, with those ideas in mind, look at these next 2 equations and just tell me, what would you expect the entropy change to be for this first one? Negative. Why? You have 3 moles of gas and you're becoming 1 mole of gas, right? So that's going down. How about the next one? Positive. How come? You're taking 1 mole of solid and making 3 moles of ions, little smaller pieces, so you'd expect the entropy to increase. So, whenever there is a spontaneous event that takes place in the universe, there's going to be an increase in entropy somewhere within the universe. It's not always within the system. Like I said, they cleaned up the family room, but the closet was a hot mess when they were done. So, when we talk about entropy, we sort of define it at absolute 0 Kelvin. And that is where the entropy of a perfectly ordered crystalline system is equal to 0. We say that absolute 0 Kelvin, is where, as low as we can go, it's where all molecular motion stops. So if all molecular motion has stopped and we have a perfectly ordered crystal, then we have 0 entropy. There's no chaos or anything. It's quite well organized. Now, you remember this superscript 0 that we talked about. Our standard thermodynamic conditions, 1 atmosphere, 298 Kelvin. We use the superscript. So we can talk about the entropy of these systems. The standard entropy change is equal to the final entropy minus the initial, or for us in chemistry, products minus reactants. So we can calculate information about the standard entropy of formation. Now think back to Chem 111 when we were talking about energy and the Hess's law. Do you remember the introduction of the standard enthalpy of formation? And for those of you that always like to balance equations with whole numbers, I told you your gig was up. You had to start balancing with fractions. Because when we have a standard reaction of formation, what are the criteria for that? Do you remember? The 1 mole of product And all of the reactants are elements in their natural states. So this holds when we're talking about the standard entropy of formation. We do this the same way. So the standard entropies of formations have been tabulated for you in the textbook on page 885. Remember, that's my page 885. Your page numbers are different. So then we find the standard entropy change by subtraction. If it's a standard entropy of formation, then we use the subscript F. And I've included a chart for you in the note packet to make it easier to find, and you don't have to carry the book around. So when you look at this, what you might notice is that there are a few elements listed on here. And do you see, if you look down near the bottom where it says chlorine, I know you can't read it on my copy, where it says chlorine, this is 223 joules per mole Kelvin. Remember, the enthalpies of formation were 0 for elements, because how much energy does it take to make an element in its natural state from its element in its natural state? It takes 0 heat. But the entropy is a measurement of the randomness and chaos. So if you have chlorine gas hanging out in its natural state, it has some chaos. Look at iron. Why is the entropy of formation for iron less than chlorine? Because it's a solid. It's just sitting there in its crystal lattice. So this is something we're going to use for reference as we go through these problems. These might seem a little bit easier than what we've been doing because this is real similar to what we did in Chem 111. Remember, in Chem 111, we calculated standard enthalpy changes. We grabbed the tabulated data, we looked at it, and then we said products minus reactants. We're going to do the same thing now, but we're going to use a chart labeled entropy instead of a chart labeled enthalpy. But we're doing exactly the same math. So calculate the standard entropy change for this reaction.